Okay, welcome to session 3, Challenging Regions, Arctic and Coastal. And I'm going to let my co-chair, Jean-Philippe, introduce Dr. Lu, since it's his postdoc advisor.
Yep.
So go ahead.
Yes, so welcome everyone. So it's my pleasure to introduce Dr. Youyu Lu, senior researcher at the Bedford Institute of Oceanography in Halifax. Yep, so if you want to be hard on questions, then be my guest, because he's my former supervisor. So, all right, so Youyu, the floor is yours. Thank you very much.
Thank you. Good morning. It's my first time to join this conference. I really enjoyed and learned a lot in the last few days. And so more from the user side and see. Okay. Short. So I'll talk about the ocean temperature variations of the coast of Nova Scotia, and based on analysis of in situ and satellite remote sensing observation, also high resolution ocean models. And I'll try to develop some applications based on the analysis of ocean temperatures. It's a teamwork. I had many collaborators with my team and others. So I'll mention their names during the presentation. So for motivation, I draw your attention to the text I highlighting in red. And so as we all know, ocean temperatures are observed with satellite in the in situ platforms. And this data can be taken as truth, but usually has gaps in space and time, and usually contains bias, noise. Ocean models provide hindcast forecasts and climate projection for future changes. And models usually have higher spatial and temporal resolution, but models usually contain bias. And if we, most people do the quality control of the observational data and do the validation of the model data, and then reveal many multiple space-time scales of ocean temperature variations. And some of these aspects of this variation can be linked to the marine fishery and ecosystem. And the question to us is, can we do more analysis and to reveal such such links, and for understanding the past changes and predicting future changes in marine fishery and marine ecosystem fishery. So that's my motivation. And so for this presentation, I'll show some examples for the recent and ongoing work, also my group, mainly in the fishery oceans. And so I will try to show 4 examples if I have time. And the first step is about comparing the surface marine heat wave parameters from remote sensing and high resolution ocean models. I will emphasize their similarities and differences. Second, about rapid cooling in the nearshore waters and during cold air outbreaks. And I will emphasize these happen on very small spatial scales, and they will be hard to resolve by ocean observations and models. The third example is about coastal upwelling, and we look at the ocean temperature, try to diagnose upwelling, and look at the interannual variations, and through a combination of the surface, the SST and winds. The fourth example is about the bottom temperature, and not from the satellite for sure, but from the ocean model and observations, and to link the bottom temperature variations with the lobster catching rate along the coast of Nova Scotia. So this is, we had quite a few presentations yesterday about marine heat waves. So this is a very simple study we recently published in Frontier Marine Science. And so we are focused on the Northwest Pacific, the coast, the South China Sea, and the coastal region. And so we compare 2 sets of the results. And from on top is the glorious 12 from the Mercantile Ocean or from the Copernicus in Europe. And the bottom is from OISST, I think the version 2.1, so one of the early versions. And so we look at the 5 parameters in the total days, frequency, duration, the mean intensity, and cumulative intensity from left to right. And so look at spatial patterns. Obviously, they're mostly, you can see a lot of similarity. But some parameters you can see there the magnitude are different. For example, on the left column is American total days average for 1993 for 2019 for each year. And so the glories have higher values and then the OISST. And similar for the durations in the third column, and also glories is higher than the OISST. And for frequency and others, there's is similar magnitude. And for mean intensity is the fourth column. And the glories, if we look at the lower latitude, south of 20 degrees south, and glories have lower values, and it's more blue, and then the deeper blue than the light blue from OISST. And so there are differences if we look at a different data set. So these are the internal variations for these parameters. And we are looking at the annual statistics. And for 5 regions, from left to right is South China, is Yellow Sea, and Sea of Japan, and crucial regions, the South China Sea, and the lower latitude North West Pacific. And all these years, you can see there's a lot of similarities. And in terms of variations, if we look at the total days on the top row, and you can see if you look at the crucial region in the third column, and South China Sea and lower latitude Northwest Pacific, there are some high peaks. And these are high peaks usually happen during the strong El Nino years. I know there's some link to El Nino in this region. And so they're mostly this peak in agreement, but again, the glories in red have the peaks are higher. And so if you look at the mean intensity, and we said on the 1, 2, 3, 4, fourth row, and in the lower latitude, you can see the red is below the blue, and which means glories get a lower intensity and than the OISST. So we want to a little bit look into what the difference in the data. The two actually now we look at 3 different types. So on the left is glories, on the middle is OISST, on the right is called a climate forecast system. Some like the NOAA results. And if we look at the upper wall is from the crucial box on the box is on the left, and you can see they're mostly similar, and glories on the left tend to be smoother and have less high frequency variation. So they have the influence on the statistics on the heat wave, but the seasonality or type is very much the same. And but if you look at lower latitude box, the difference is much bigger, and so. Glories is much smoother and has much less high frequency variations, so we have longer durations for marine heat waves. And OISST is have more high frequency fluctuations, is up and down, and CFS is kind of in between, but closer to the OISST CFS. So I guess the question is we don't quite understand what causes the differences. Are these due to some of the noise in the satellite data OISST, or in the data simulation models for the glories? So we needed to I think the audience may have a good idea to ask, but they certainly, if the model may have issues or data may have noise that may affect these high order statistics and for our simple study. So this is a more recent analysis on marine heat waves, also the cold spells or the negative heat waves on the Scotian shelf. So we have seen 2 years. On the left is 1997, which is a cold year, and both on the surface and the bottom. And you can see the blue is the climatology average over 30 years. This is from glories, and we also compare CMC-SAT, get similar results. And so this year, the climatology, 30-year average climatology is in blue, and the temperature is mostly below the climatology, is a cold year. And similar for the bottom. Bottom is a black curve is from glories. And so So the blue is climatology, the green is 90% percentile threshold. So this is a cold year, and you can see the more chance to get a cold spell than marine heat waves. On the middle is 2012, which is a warm year. And so the temperature is above the climatology, or both on the surface and also the bottom. And so you can see there's a more chance for the heat waves. And we look at the spectra, and so on the top right is the CMC SIT in blue. That's yesterday our colleague, ECC colleague, introduced a CMC SIT and in blue, and also the Glorious in red. So the spectra is quite consistent. So that's encouraging at one location near the coast. And for the bottom, and so Glorious in red, and mooring data in blue, and you can see some differences. So the model certainly you can see difference both in the high frequency, and so the mooring has more high frequency variations, and but the Glorious has more large low frequency variation. So that's my point. So when you look at these high order statistics, you need to if you use model data, and you know the model may have some issues for this kind of application. But I know my colleague Peter Gabriel in the audience, so he used a lot of the observation data, mooring data, to look at marine heat waves. So if you look at the spatial pattern, and for we look at the marine heat wave parameters, 3 parameters. I think the frequency on the left, the total days on or the duration I forgot in the middle, and the mean intensity on the right. So on the surface in the first top row, and the bottom is the lower row, and you see there are a lot of spatial patterns. And these are patterns we are trying to explain with either we know the circulation is correspond with the circulation or mesoscale eddies, and associated with the Gulf Stream in our region. And when you see the bottom, you can see the topography has effect, and look at the bottom right. So there's a look at the bottom is much quieter in the deep water. And so there's, they should be, I didn't look hard, consistent with the observation. And so we are trying to, I think it shouldn't be too hard to find the physics for this kind of a spatial pattern. And the internal variations, and again on the surface is on the left, and the right is the bottom, and the upper 2 rows is for the surface heat waves, and the MCS is the cold spells in the 3rd and the 4th row, and bottom is just temperature, the surface temperature and the bottom temperature. So this is regarding this. You can see there. So yesterday we talked about the definition of the heat waves, also called cold spells. So if we define the climatology over 30 years, so then the variation, the long-term variation or the trend in the heat wave or cold spell parameters is related to the definition. So and the bottom example is the bottom right is a bottom temperature is red is Glorious, and the blue is mooring observation. And as we know, they're on Scotian shelf. So there's a kind of temperature, there's a kind of regime change from the colder area, and before 2012, after 2012, the bottom temperature is higher, and is maintained. There's up and down internal variation. But then you look at the marine cold spells, it's mostly happening between the 2012 and marine heat wave is also mostly after 2012. So this is very much, yesterday I think I learned a lot. So, do we need the detrend? How we do the detrending, and to make sure there's these heat wave or cold spells statistics is not kind of separated from the low frequency or long-term temperature change. And so again, I very much agree with the comment. So you really need to look at who care about heat waves or cold spells. So we know some example by the fish physiology, like heartbeat, and also there's some studies on area, and also the motion of the fish, and there's influence. So that definition, how to define the heat waves, the cold spell have to link to the application. So we're working hard on that aspect. Second example, so just we watch the time for me, so I try to get faster. So there's a called rapid drop of ocean temperature and in the nearshore water during cold air outbreaks. This is last year, and in February, is over the weekend. It's a short 2 days event, and this is a temperature record from the airport near Halifax, and so you can see their air temperature is certainly starting to drop. So I certainly remember how cold that day, that weekend was. So we know when cold air outbreak is origin from Arctic is more large scale. So it's cold in Halifax, it's all cold in Montreal. So there's large scale cold cooling. Also, there's some time lag. But what about the ocean? So we know the ocean and ocean. So where seas coming more like more spatial scale. So this is from the Southeast model. The results from my ECCC colleagues. So it's just sort of after event. So my group, we look at what the ECCC model tells. So this is on the February 2nd is before the cold air outbreak and after on 25th. So you can see there's certain the Gulf Stream and Gulf Sonora, there's some different, but look at the difference. So difference is left minus right. You can see the temperature change, and there's a change on the smaller scales. And near the coast of Nova Scotia, it's this kind of lobster ship thing, and so you can see it's mostly the cold temperature or the temperature drop happening near the coast, and can come to a few degrees, maybe like 3 to 5 degrees, and all these bays, shallow bays. There are also some large scale fish feature, and we can other hand we know the physical reason. So the thing is that we stop moving. Okay, and I have a colleague, and so now is we know the model. We need to see are the model realistic. So we pull up many coastal nearshore observations, which are the blue is observations, and so we can see the red in the model, and all these coastal stations are on the map on the top right. And you can see, well, there's some similarities. The model captures some, for example, in the Lunenburg, in the left, in the middle one, and you can see the magnitude of the temperature drop during this event is very much the same. The model matches quite well, and of course the model the model have a kind of a code bias. So that's a bias. We look at the change, so they're consistent. But some other locations, if it's a Port Hawkesbury and on this location and sure the cursor worked. And you can see the model, the observation is much bigger, have a larger the temperature change, but the model just barely sees the small change. So we know this model is not perfect, and some can be related to the model resolution. This model is the CLP is a 2.5 kilometer resolution, and our shallow bay is just a few kilometers wide. So you can know they're challenging for the model to resolve this the small bays. But then you can also imagine this will be hard for observations both in situ and satellite to resolve this kind of small spatial scale variation. So who cares about this? And so this is the event earlier, I think when, so in 2016, there's similar event, but happened in December. And so again, in the base, in the CLP results, we produce the temperature drop. And there's around those events, there was in the media and talk about this, a massive fish kill event. And so in the base, so we know there's, we are not confirmed, we're sure, and the cold temperature caused the fish kill, but we are just a bit from future study. Okay, I need to be a little bit faster, and so have time for questions and comments. So the third is about the intermittent variation of upwelling on the coast of Nova Scotia, and so this is also the working process. And so here we base on Gloris because we look at a longer time series from 1993, and so the definition of upwelling. And so our coast is not that easy and just use temperature because there's also current along the coast, brings the water from the Gulf St. Lawrence. And also we also want to focus on the season. The upwelling can impact on the phytoplankton bloom, for example. We know how the bloom happened in spring. So we're focused. So we have a combination of definitions, the wind index and wind be favorable for upwelling, and surface temperature. We use the offshore and the coast and near shore, see the difference. And we also look at the difference between the surface and the deeper layer temperature, but we also want to relax that's really because we want basically, can we just use a SST and wind to derive upwelling index? So with this, they tend to be harder than we saw in the beginning, but for all this combination, we get this kind of time series. On the left is more like we have every grid point. When we integrate, we get upwind area. And the horizontal x-axis is the year, and the vertical axis is the month. So it's more like you look at this, you can the seasonality, the change. So it's where you lose quite a noisy field, but if you average, and you can get like this, like both area intensity has this kind of seasonal cycle. For the variation, it seems to make sense, and also there start interannual variations, and there's interannual variations, and there looks significant. We need to statistical test to there. So more important, we want to link to the phytoplankton bloom variations or others. You will need to work on the fishery ecosystem researcher. So this is work ongoing. The last example is bottom temperature variation during the 15, 16 years at a link to the lobster catching rate. So we know this the temperature is varying, and we have observation data called the Atlantic Zonal Monitoring Program. And so this is the bottom temperature. The anomaly defined. So we know that 2011, 2012, these are in July, is a warm anomaly. It's across the whole shelf. And look at the interannual variations from 1990. This from the model which is glorious, and I think or other model, and then the red is the example observation there for July. There is some consistent variation. And so there has come confidence about the models. And so then we look at this lobster fishing area, and the color not great, and focus on the coast. There's so 1, 2, 3, sorry, in the dark blue is on the coast, and 4 is half the coast and also offshore, and 5, 6, 7. These are 5, 7 polygons. This is the fishery scientists have the data for their fishery catching rate. And how the data looks like. These are the global temperature in gray, and for this, you can see the bottom temperature there kind of quite a bit internal variation, some seasonal signal, and the green dots are the fishery, the lobster catching rate, and you can see there's some seasonal pattern. We know why, and there's also some internal variation. And there are different ways to look at if you look at the correlation, there are different ways to look at that we need to closely work on the fishery colleague for that. So this is a very simple analysis, and we did, I think the black is the bottom temperature on these polygons, and the green is the lobster catching rate. So the temperature is average for November, December, and the fishing season we average from November to April, and so there's lobster starting in November and finish the fishing in April. So these are with these years, this annually, we just see curves. There are some curves have higher resolution, like number 5, 6, or 4, 5, 6. 7 as a correlation can be like about 0.6 or 0.8 because it's correlation. But so there's look at the number 4, and there's both bottom temperature and lobster catching rate have upward trend. So this could be due to the trend, the correlation. And so if we remove the trend, and some location number 1 before is not high, now become the higher correlation, but some location number 4 is not virtually have no correlation. So there's the story not quite clear, and we need to understand why there correlation in some location and the no correlation in other regions. So this we need to closely work on the people understand the lobster catching rate data and the physics. So it's a summary. So remote sensing have different high, and SAT have different high frequency statistics with the models, and we need to understand why is that. And the model and observations will have challenges with a small spatial scale temperature. And I think I learned there's new products that can be solved some of the issues. And quality control validation tell accuracy bias of observation models. And this is very important for decide where, at when, at what scale, and we can apply the temperature data for application. And these multiple aberrations, they have different aspects for the marine ecosystem fisheries. So we need to closely work with colleagues outside our field to work to look at the relationship. And applications will benefit. This is very important. Continued development of the observational data and also high resolution ocean model data from remote sensing in situ observation and model. Thank you very much, and look forward to your comments or questions. Thank you.
So we have time for questions.
You have time, right? I want to get something. Sorry, it's a bit long.
Okay.
All right, thank you, Youyu. One question is for the last study that you've been working on with the bottom temperature and the lobster catches.
Yeah.
Did you do any type of correlation with the sea surface temperature? Like if there's any information on the signal that you can get from the DSST?
Yeah, I think that's temperature is all, that's very nice question. It's all important. So when we do not have the observation, like bottom temperature is rare, mooring is so scarce. So we need to build the confidence from the upper, the surface temperature and from remote sensing. You have a large, good spatial and temperature scale. So we build that. And Scotian Shelf is kind of a hard place because that's why we don't have much predictability for the for this the change of temperature. Surface we know there can be from the RC fluxes, and they're also lateral. And these are the water come from the lateral current that goes from Grand Banks of Newfoundland, and also from the Gulf St. Lawrence come to the to us along the coast of the North South Current, and also the offshore. The offshore is the Gulf Stream is very offshore, and between the Gulf Stream and the shelf, they're called the Scotian Slope. And those waters more like a mixture from the Gulf Stream water and the cold water from the Labrador Current goes from the Grand Banks. So these are mixing process is very much I would say it's very nonlinear due to the eddies or also the eddies also the Labrador Current that go around the Grand Banks is also very nonlinear. So it's very hard to predict. And some of the signals we know there's some signal are due to the what happened in the Scotian Slope. And so is there some are surface and some are lateral and some are upstream, some are offshore. It's a very challenging place for both for the model for prediction. Yeah.
Thank you. Any more questions? Yes.
There's one there.
Thanks for the talk. Peter Galbraith, Fisheries and Oceans Canada, so a colleague. Far away from SST, but I think for snow crab, it might be interesting to look at bottom area lower than threshold temperatures like 0, 1, 2, 3, 4, so forth.
Yeah.
So.
Peter Galbraith is a senior scientist in the DFO in Quebec, and so I have lots of respect for Peter. And so he look at very hard on the data, observational data, and also he look at some marine heat wave statistics. So I think I only start more recent years more, start to talk to the fishery scientists, but for Peter is more his career, and so much can learn. So again, so very much I think it's all ground fish and all this, so Peter, all this work, I need to very much to pay attention to your papers and also your colleague. I know some you also link to the models, with the people in the Quebec and the ECCC. So I will try to work with you on this, to refine the analysis. Thank you very much.
Okay.
Yeah.
Thanks.
It's online.
Anybody else?
Okay, thank you very much.
Let's thank Dr. Lu again. So our next speaker is Gary Corlett from EUMETSAT.
Hey, good morning, everybody. Yeah, so I'm Gary Corlett. I'm a remote sensing scientist at EUMETSAT, and I work in a surface temperature radiometry group along with my co-authors, Anna Carroll, who is here in the room, and chair of the GRIS science team, and Igor Tomazic, who unfortunately is not able to attend the meeting this year. So I'm going to talk to you about some evolutions we're planning for our Copernicus SLSTR sea surface temperature products. In particular, the evolutions come in two categories, and they're very relevant to the coastal and high latitude zones. So we're going to be releasing the first collection 4 products, hopefully next year. The product has been very stable for some time now at collection 3. So the evolutions, you may have heard me in the past talk about day 1 and day 2 differences. So this is EUMETSAT parlance for sort of first versions of algorithms, which are normally available, of course, when the satellite's launched, hence to day 1 parlance. And then major evolutions afterwards would be day 2, day 3, etc. So the two evolutions are the SST day 2, which will have big improvements, particularly in coastal zones, due to updates to the Bayesian cloud mask. And then we have a new combined SST and sea ice product, and this is the IST day 1 product. So at the moment, we've been involved with much of the prototyping, and we now have pre-operational products available from the Copernicus Wikao cloud environment. So these have been available now more or less with approximately 6-hour timeliness since the beginning of April. And if you want more details, please see the web link there, and it'll tell you how to get access details. At the moment, we're hoping for deployment operationally in spring next year, but of course that's subject to confirmation, and of course the Sentinel-3 sea launch date uncertainty, which was discussed previously. So the improvements in the coastal zone are primarily changes to our Bayesian cloud mask in the daytime only. So these changes I'm going to talk about are only applicable to the daytime data. And this was the work of a study led by the University of Reading. More details can be found. Oops, wrong one again. I knew I'd do that. In the paper referenced here, led by Claire Bulgin from the University of Reading. In principle, the main change is rather than to use the thermal channels, we're now using the visible channels for the textual test. And this has a big improvement in removing certainly fronts as well that are overflagged. And then there's one particular example from the study report, which you can find from the EUMETSAT website. We see the operational mask here, where most of the Bohai Sea here, which is of course has very high sediment and is normally flagged as cloud. Now, by using the visible channel standard deviation, we get a big improvement, and now we're not overflagging all of these sedimentary waters. So this is quite a big improvement. Part of this has been an update to improve the co-registration between the visible channels and the thermal channels. So the visible channels are now giving a much better representation of what the thermal channels are seeing radiometrically. Two more examples. These were provided by the CMEMS SST TAC. So on the top, you see, unfortunately, it's an inverted image of the Mediterranean. So on the left, is the operational cloud mask, where we see a lot of overflagging around the coasts, particularly around Sicily, and in the new collection 4 products, this has been removed. The third example there, although not specifically for coastal regions, shows you now the advantage as well for fronts, where previously most of the fronts were flagged due again to this use of the thermal textural test, and this is now not the case for the collection 4. One thing I would like to point out, though, is there is still some persistent flagging in this particular area here, and this is actually an injection of cold water into the Gulf Stream, which is nearly 10 degrees colder than the surrounding warm water, and unfortunately the cloud mask is still detecting this as cloud. I did check on this particular day most level 4 and other satellite level 2 and 3 products, and this injection is not visible in any level 4 analysis, and that's because it's nearly always flagged as cloud in many products. From the discussion yesterday, I would have to let Owen know, though, that the CCI did not flag this as cloud, and the advantage was it uses a dual view Bayesian in this particular pixel. So that, given yesterday's discussion, I thought was quite relevant to say. We're also adding SST depth to the product. So this is now to give you an estimated temperature at roughly 20 centimeters, which is that equivalent, we think, to a drifting buoy. And this is using a combined skin effect diurnal variability model. At the moment, we're using the UK Met Office implementation, but we are working with NOAA and with their experts to revise this. We're also now including uncertainties in the form of a total uncertainty and its components. And at the moment, this is not specified in the GLIS format, but we're adopting the CCI implementation for this, as at the moment, this is the only other product that does this. And we would certainly suggest that users use the uncertainty information rather than the SSES, because it will give you a much better understanding of the error fields. So the sea ice surface temperature combined product is a new product. So this will be the first time we've deployed this for SLSTR. The example animations on the right-hand side show you at the top data from SLSTR-A and at the bottom from SLSTR-B. On the left-hand side is the nadir-only product, and on the right is a dual view. And this is just data from April this year showing the daily averaged combined ice surface temperature. Although the product is combined SST and IST, in this particular example, I'm only showing you the IST. And it's very interesting. It's giving reasonably sensible results for a day one product. And actually, if you look at the variation of the ice surface temperature over the Arctic, over just that 1 month, there's nearly a 15-degree change in the temperature. And it shows you how important it is to monitor these areas. The product itself is developed by DMI and by Metno. The algorithms are shown on the screen. So the product either contains SST, which is the same SST as our SST product, or it'll contain an estimate of sea ice surface temperature, or for certain cases where we think we have mixed ice and water, there is a marginal ice zone temperature. We're aiming for the GCOS accuracy requirements, and the early results from the validation, which you can find in reports on our website, show that certainly for SLSTR-B in daytime, we're already very close to the GCOS requirements. So we're quite pleased with the developments. For the cloud masking, we are using, as you have already seen from other talks, the EUMETSAT NWC staff PPS cloud mask. This now, as well as having the basic cloud mask information, also has the cloud probability, and some work led by Steiner at Metno has defined an algorithm now that uses both the cloud mask and the probability to give a better product. And you saw the other day in the cloud mask task team report how well the product is doing. And this is why we have fairly good confidence in the product. As a result of the new product, there are some GDS evolutions. I think we'll obviously come back to these later in the week. So certainly expanding the GDS now to take into account products with different depths and also different types. If we have sea ice surface temperature and IST is essential. So this is one thing we want to add. And also at the bottom there, we would like to add a couple of other extra fields, including the uncertainties. As I said, at the moment, uncertainties are really the way forward for us, and these should now be specified in the GDS. There are still some ongoing activities. So for the SST, we're still looking to refine the Bayesian cloud mask. We still have a particular problem in the oblique view in identifying sun glint, amongst others. We'll also still to refine the PPS cloud mask for the sea ice. This one particular example on the screen shows you a nighttime RGB image at the top right, and then the resulting cloud mask underneath. So there are cases where the nighttime cloud mask works very well, and I just happen to pick one of those, as is always in the talk, but of course there are cases where it doesn't work so well. So that's one thing we still want to do. We'll also take into account any feedback. So as I've mentioned before, the products are now available. You can download them to test them before they go operational. And so any feedback from users will also be, of course, factored in. So the Copernicus collection for sea surface temperature and sea ice surface temperature products will hopefully be made operational next year. The products will be a sea surface temperature product, WST, and an IST product containing both sea surface temperature and ice surface temperature. And this is available above 50 degrees latitude in both hemispheres. One change to the products we're now making is we're also now providing you with the full nadir swath from SLSTR. SLSTR, as you know, is a dual view radiometer. So there will be a dual view product if you only want to work for reference applications. And then there is a single view product, which for more slightly wider swath applications, if you're looking at gradients or things, will be much more beneficial. So the products are now available in pre-operational data. If you need access or if you have any questions, obviously please come and see me at the meeting. And with that, I'll say thank you.
So I don't see any questions online. Do we have questions here? Yeah, John, go ahead.
A very quick question, but the implication is if you're using visible daytime texture to remove cloud in the daytime, at night you don't have that. So are you kind of going to get a toggle effect where nice, clear, whatever, and you go into the infrared and it's all cloudy? Or
Quite possibly, yes, unfortunately.
Yeah.
We at the moment, we have to use the thermal bands for the textual test, and it's really not possible to turn it off, unfortunately. So yeah, there will be a slight change, yeah. But at the moment, yeah, unfortunately, we don't have a solution to improve the textual test at night time.
So is there a local variability threshold function in the textual test or not?
In the PDF, yes.
Okay, for the spatial.
Yeah.
Okay, because I mean, obviously, if you're then retrieving better SST gradients in the day, you could feed that in and relax the test on those frontal boundaries, maybe. I mean, it's a lot of work, but
possibly, yeah. That's there are things to be looked at and things we've been in discussion with.
yeah, and also machine vision is quite good at detecting fronts.
Sorry.
Machine vision is quite good at detecting fronts.
Okay.
I mean, Arena and people have done stuff on that. So.
Yeah.
Okay.
Yeah.
Jorge.
Thank you, Sandra. Thank you, Gary, for that talk. Just a quick question. You mentioned the GDS. Do you foresee that in the future, for example, the sea ice product would be the standard for applying to grist in general? Because I think consistency in the Arctic is so critical right now.
Yeah, I think absolutely. Yeah, and I think it's easy to fairly straightforward to include with the correct flagging. It's just a matter of the small details, which of course, as you know, in these things count. And I think Jeff and others will be leading on this later. But yeah, combining the sea ice surface temperature with the SST is very important. Yeah.
I have a question, Gary. What are you guys doing to guarantee consistency between SST and ice concentration at the marginal ice?
So at the moment, we're only using the information from the sensor. So hopefully it should be at least consistently wrong, if that makes sense. So we're not using alternative external information at the moment. So we're only using the imagery of the data. So if we correctly flag it as being marginal from the information we have, because we do have sub-pixel resolution from the visible data, then that would be wrong. Of course, that classification could be wrong still, but then it would be, yeah, at least inconsistently wrong, if that makes sense.